So finally, let's talk about the hyperbolic Pythagorean theorem. So here's a statement. Let ABC be a hyperbolic triangle with a right angle being at the vertex C. If we denote the lengths, the hyperbolic length of the hyperbolic sides, remember hyperbolic triangle does not consist of straight line segments, some of them are bowed, so these are geodesics on the hyperbolic plane. So if A, B, and C are the hyperbolic lengths of the sides, opposite to the vertices A, B, C respectively, then hyperbolic cosine of C is equal to the hyperbolic cosine of A times the hyperbolic cosine of B. Immediately before I start this proof, I want you to note the striking similarity to the Pythagorean theorem on the sphere, which essentially said something like this. With the similar assumptions, cosine C is equal to cosine A, cosine B. So you see that the hyperbolic sine and cosine, the hyperbolic trigonometric functions, play essentially the same role as the trigonometric functions did on the sphere. Very similar statement. Okay, so let's get to the proof of this theorem. I'm only going to prove this theorem for a right triangle in the so-called standard position. Standard position means that the triangle is here, A, B, C, so one of its sides falls on the y-axis, and the right angle is the angle at the right axis. This does not really any loss of generality, because one can prove that using a sequence of rigid motions on the hyperbolic plane, any right triangle can be brought into a standard position. We have not talked about all the hyperbolic motions in this course, so you have to trust me on this one. That every right triangle can be brought by a sequence of rigid motions to a standard position. Okay, so let's start the proof of it. So as I said, we assume, so this is without loss of generality, that ABC is in standard position. Is in a standard position. So we write A as 0, k, so it lies on the y-axis, so the x-coordinate is 0. C as 0, L, that's where the right angle is, and B will be S, T, some point here. Okay, we also denote the angle opposite A by alpha. Sorry, not opposite A, at A. The angle at A by alpha. And the angle at B by beta. Okay, so now we have this triangle here. Let D equal to negative D comma 0 be the center of the bowed geodesic AB. This is a hyperbolic side of that triangle. Because A and B are not vertically aligned, this side is part of a circle whose center is somewhere on the x-axis right here. Okay, so that's D, whose coordinates are negative D comma 0. So we denote the radius by R. So this here is a sector of that circle. This is R, and that as well as R. Similarly, we get the purple sector here, the purple sector. So similarly, so that L be the radius of the bound geodesic or maybe I shouldn't say let L. I mean, I already told you what L is, so it's not. I don't get to give it another designation. But I want to note, right, the geodesic that goes through points B and C is an arc of a circle whose center is the origin. It must lie somewhere on the x-axis, and its center will be below this. The point C. So note that the center of the geodesic joining C and B is O, the origin. I mean, why is that? That's because this angle here is right. Yeah, so that means the angle formed by the y-axis and the tangent line to this circle going through C and B is 90 degrees, which means the tangent line to the circle must be horizontal. In other words, this is the top of that circle that connects B and C. So that means the center of the circle must be the origin here. And its radius is L. Okay, now by one of the previous videos where we actually described how to find angles between a vertical geodesic and a bowed one, you know that the angle alpha in this triangle, which again is really the angle between this vertical line and the tangent line to that red circle, alpha can also be found here, the ray connecting this. Similarly, if I draw a vertical geodesic going through the point B, the angle between this vertical geodesic and this bowed one, which is again the angle between this and the tangent line, can be found over here. So let's just write this down. So note that alpha is the same as the angle ADO. And if we write, so I guess I maybe want some notation for this orange geodesic. How about I call it N? And if N, and if we write N for the vertical geodesic segment, above B, then the angle between the geodesic AB the geodesic and N, which I define to be beta 1, is equal to this angle BDO. Okay, so I'm not going to erase this picture. So in the lecture about preparation to the Pythagorean theorem, we proved a certain formula for cosh, hyperbolic cosine of sides of, hyperbolic cosine of a length of bout geodesic. So here I'm going to be interested in this geodesic A. So in the previous So in the previous video, in the previous lecture, we proved that so I want the cosine of hyperbolic cosine of A, that is equal to, so what was the formula? The formula was 1 plus cosine alpha cosine beta, so it was 1 plus cosine. Okay, so this angle is right, and this angle is beta plus beta 1. So it's 1 cosine beta plus beta 1 cosine 90 degrees divided by sine beta plus beta 1 sine 90 degrees. Okay, this was, remember, the formula for cosine of the length of a geodesic between two vertical geodesics. And the angles, the interesting angles here were this angle, which is the angle between the bout geodesic and one of the vertical lines. For us, it's beta plus beta 1. And the other angle here for us, it's right angle. Well, cosine of pi halves is, of course, 0. So this gives us just, and sine of pi halves is 1. So that just gives us 1 over sine beta plus beta 1. So that's cosecant of beta plus beta 1. And what is that on the picture? Cosecant of beta plus beta 1. So where is that that triangle? So beta plus beta 1 is going to be this angle over here. So that is equal to L over T. Okay, so we're looking really at this. I don't want to make the picture even harder to see. Looking at this right triangle here. This right triangle here. And the claim is, so we're looking at cosecant beta over beta 1, in other words 1 over sine beta over beta 1, and beta plus beta 1. So that is saying that, so this angle here is the same as beta plus beta 1, again by the same logic as before, right? The beta plus beta 1 looks kind of bigger on this picture, but you see this picture is not really telling you the truth because the angle beta plus beta 1 is really the angle between the tangent line to the purple line and the orange line, right? And the tangent line, so that will actually make a little smaller angle here. And again, the tangent line to this circle is perpendicular to the radius. So if you do the calculation, then you see that this is the same angle as that. And the cosecant of beta plus beta 1, that's the hypotenuse, so L divided by this far leg, the opposite leg. So it's L, and the length of this leg here is T, because that's the y-coordinate of the point B. Okay, so we have that. Now, so that's one of the sides, or hyperbolic cosines of one of the sides. Let's look at another one. Maybe let's look at B. B is easier to compute because B is part of a vertical geodesic. So that's just natural log of the y-coordinate of the point on the top divided by the y-coordinate of the point on the bottom. So that's natural log of K over L. Okay, so I'm going to compute. Remember, what we're trying to do, right, is we're trying to show the Pythagorean theorem, which gives you, it tells cosh of C is equal to cosh of A times cosh of B. So I'm trying to compute all these hyperbolic cosines. So I already have this one. So now I want to know cosh of B and then still cosh of C. So what's cosh of B? Well, that's of course, e to the b plus e to the minus b over 2. So e and natural log cancel each other, so that's k over L plus, well, this is 1 over e to the b, so that's L over k divided by 2. So if I get a common denominator, Lk, then I get that this is equal to k squared plus L squared divided by 2kl. Okay, so I have cosine, hyperbolic cosine of A and hyperbolic cosine of B. So now let's work on hyperbolic cosine of C. Let's just write this down here for ourselves so we remember for later that that was hyperbolic cosine. That's cosh of A. Alright, so finally the hyperbolic cosine of C. So that's this length here, the red length. So hyperbolic cosine of C. What is this? Again, I am using this formula from last lecture. So that's 1 plus cosine beta 1. Again, the angle between the geodesic and the vertical geodesic. Times, and now what about the other one? Well, where does this other geodesic intersect the y-axis? It intersects it here. So the other relevant angle is this one, but this angle is pi minus alpha. So again, this is so pi minus alpha divided by sine beta 1 sine pi minus alpha. Again, this is the lecture about the preparation. So proposition in preparation for Pythagorean theorem. Okay, so let's compute what this is. So I get, so it's 1 cosine beta 1. Where do I have my right triangle? It's right here. Cosine beta 1, so I'm going to use the triangle. D, B. I guess I maybe should even introduce some name for this point here. Let's call it R. So DBR, right? Triangle DBR. It's a right triangle with right angle at R. So cosine beta 1, that is that length over here divided by R. So what is that length? That length is D plus S, right? S is the x-coordinate of point B. So that length here is S. And this length here is this length here is D. So I get D plus S. So 1 plus D plus S divided by R. And what about cosine of pi minus alpha? Well, that's the same as minus cosine alpha. So minus. And what's cosine alpha? Well, here I'm looking at the triangle DOA. So and triangle DOA. So this cosine is going to be D divided by R. Minus D divided by R. Okay, what about the sines? So sine beta 1, that's this length here again, so that's T divided by R. Times for sine pi minus alpha, well, that's the same as sine alpha, right? That thing is the same as sine alpha. And sine alpha, that's going to be this length, so that's K divided by R. K divided by R. All right, let's see what we get here. Common denominator R squared, so we get R squared plus d plus s d. Sorry, not plus, but minus. R squared minus d plus s d over r squared, right? That's the numerator. R squared d plus s times d over r squared divided by tk over r squared. So now the r squareds cancel, and I get r squared minus d plus s d divided by tk. Divided by tk. Let's work it out even further. So that's r squared minus d squared minus sd divided by tk. But r squared and d squared, where are we with those? This triangle here, right? R squared minus d squared by the Euclidean Pythagorean theorem gives you this length, so k squared. So I Euclidean, so standard Pythagorean theorem. For the triangle DAO, we get that r squared minus d squared is equal to, so r squared minus d squared is equal to this, which is k squared. So we get the formula for cosh C to be, so r squared minus d squared is k squared minus sd over tk. Okay, so here are our three candidates to compare: cosh C, cosh A, and cosh B. And the claim is that if I multiply cosh A by cosh B, I get actually cosh C. Let's see that that's true. So again, by the Euclidean Pythagorean theorem, we get that s squared plus t squared is equal to L squared. Let's check that. S squared plus t squared is equal to L squared. Nothing strange there. And we get s plus d squared plus t squared is equal to r squared. S plus d, that's this big thing, plus t squared, so that's this little one, is equal to r squared. So from this, we get that 2sd plus s squared plus t squared is equal to k squared. Sorry, did I do something wrong here? Yeah, one more equality. R squared is also equal to d squared plus k squared. D squared plus k squared, we already looked at this triangle, also gives you r squared. Okay, so from this one, what do we get if we do the squaring here? So that's 2sd plus d squared plus t squared is equal to d squared plus k squared. And cancelling the d squared on both sides, we get that we get the 2sd plus s squared plus t squared is equal to k squared. And so from this further, we get that 2sd plus L squared, this thing is equal to L squared by that equality over here. So this is equal to k squared. Okay, so finally from this we compute SD, and that's k squared minus L squared over 2. All right, so our final calculation, for which we will not need the picture anymore. So we just combine all these formulas now. We get that cosh C, which we have over here. So cosh C, which is k squared minus SD over tk. That is the same as k squared minus, so I'm using this now here, k squared minus L squared over 2 divided by tk. So let's tidy it up a little bit. Let's get a common denominator of 2. So I get 2k squared minus k squared plus L squared divided by 2tk. So that gives me k squared plus L squared divided by 2tk. And that I can write as L over t times k squared plus t squared divided by 2kl, right? You see the L cancels on both sides of this formula, so it gives you that. But this is cosh A, and the other thing is, this is cosh B. Okay, so this proves the hyperbolic Pythagorean theorem. In the next video, we'll quickly discuss the connection to the planar Pythagorean theorem.